Hello everyone, welcome. This is my first video and today we are going to be beginning with the very first unit of AP Calculus AB or Calculus 1, aka Differential Calculus. But today we will be talking about rates of change first. This will be the first thing we talk about. Now, in algebra, one of the things you learn is the idea of the average rate of change. Now, how do you find the average rate of change of a function? Well, let's say you choose 2 points. And what you do is you essentially you find this line right here, and the slope, the line that conjoins those 2 points, the slope of this line is your average rate of change between those 2 points. And you can also write this as, let's say this is x1, x2, no, sorry. Let's say this is x2 and y2, and this point here is x1 and y1. The slope of this line is given by y2 minus y1 over x2 minus x1. This is you might recognize this as your slope formula from algebra. Now, in calculus, instead of finding the average rate of change, when we look at a function, we also want what we call the instantaneous rate of change. Now, what this essentially boils down to is if I were to give you some point on the same curve as before, and I say find me the rate of change at this point, just at that point, exactly at this point. Now, this point is kind of hard if you don't know calculus, obviously. But like, let's say I choose a separate point like this point. At this point, you can easily tell that the rate of change here is 0, because if you just draw this line here, let's say this is, assuming this is f of x equals x squared. This point here, the rate of change, the instantaneous rate of change, is 0. And you can tell that visually by the graph, but sometimes if it's not obvious, like here, there's a couple of ways you can find this instantaneous rate of change. So the first thing you can do is you can estimate the instantaneous rate of change. And what I mean by this, you can choose 2 points that is very close to this white point here, and you can find the average rate of change between those 2 points that is very close to that point. And then this will give you an estimated instantaneous rate of change for this white point. It's an estimated instantaneous rate of change. Now, obviously, this is an estimate. It's not going to be pretty. And what if you wanted to find the instantaneous rate of change throughout the graph? And that is, that's coming up later. That's the concept that that's called derivative. But for now, we're gonna teach you how to do this using quote-unquote limits. Now, you might not know what limits are yet, which is okay, that's normal. But first, before we begin talking about limits, I'm going to begin by talking about specific functions and function properties. Before this, you might have heard about asymptotes. So functions like this, where you have, let's say you have an asymptote here, and then it goes like this. And there's many types of asymptotes. It can be like this, where the functions go like that, the same way, down. It can be any way, shape, or form. Now, this is one form of what we call discontinuity. But there are other forms of discontinuities. For example, you can have this graph, let's say x minus 1, x minus 1. Now, you might be looking at this and you might be like, Okay, well, x minus 1 cancels out, so this must be x, right? That's half true. Technically, the graph, if we look at the graph for this, technically, yes, it is x. However, the thing we canceled out, what point is that? What zero is that? And that will be 1, right? If we go back to this original equation, when x is equal to 1, this becomes x minus x times 0 over 0. And this is indeterminate. Not determinable. This doesn't exist. You can't divide by 0. And so what does this mean on this graph is even though it looks like x, there is a hole at x equals 1. So let's go to x equals 1. There is a hole here. Which means that this graph is determined for every point except for x equals 1. That's what a hole is. So you have asymptotes. I spelled that so wrong, but you get asymptotes. You get that. You get the idea. And you have holes. Are those the only two? No. There are other forms of discontinuities, which I will show you right now. So another form of discontinuity is if you have some curve, let's say, let's just use y equals x again. Let's say you have a hole here, but then a point here at the same x coordinate, right? This is another form of discontinuity. Instead of it being defined along this curve, it's defined somewhere outside of the curve. That's called, I don't know the exact name for this, but later on we'll classify different types of discontinuities. Anyways, there is also this type of discontinuity, which I don't also know the name for, but you can have a function that is defined here, and then it's not defined until there, and then it's defined here, and then there's a big gap. You see, this can be this is technically a piecewise function, and if you don't know what that is essentially you can write a function that is defined for I guess technically for this it can be like between like -3 to -2, right? And then you can have it defined again for let's say this 1 and that's 2. So 1, that's not negative. 1, 2. So the idea is, actually no, this is wrong. It should be -2. No, sorry, that's correct. All right. So anyways, a piecewise function is basically a function that you can explicitly write as being defined along specific points. And you can have it stop and end anywhere, basically. And you can use any functions over here. That's basically what a piecewise function is. If you don't know, this is pretty simple. But anyways, we're gonna move on to how we're gonna define discontinuities. So there are two types. There's two types. There's the removable discontinuity, and the non-removable discontinuity. Removable, essentially what a removable discontinuity is essentially any discontinuity where the graph is not defined at like a singular point. It always looks like some sort of hole. It can be just a hole, it can be a hole with a point above it. It's defined somewhere else that's not on that point. It can be a lot of different things. But just keep in mind that it's mostly related to like a gap at a point, at one point. That's the key idea. A non-removable discontinuity would be, you might have already guessed, but it would be something like an asymptote. Let's say there's an asymptote here. Goes like this. It can be anything. It can be like this. You get the idea. But that's a non-removable discontinuity. It's not just. It's defined along like a big gap. There's some gap that's not a hole. And there's also the one I showed you before with the piecewise function, where it's defined here and defined here. These two would be removable discontinuities. This non-removable. Sorry, these would be non-removable discontinuities, and this would be a type of removable discontinuity. But anyways, this is important because these two concepts will help us define or help us calculate limits. And so, let us get to the concept of limits. So what is a limit? So let's take some graphs. Let's use a sine curve just for sake of simplicity, right? Let's say this point here, this is a regular sine curve, this would be 1, right? Y. And let's say this x is at pi over 2? Right. Yes, pi over 2. And the idea is, let's say I wanted to find the limit as x, by the way, this is how you notate limits, as x approaches pi over 2 of this function, which we'll call f of x equals sine x. So limit as x approaches pi over 2 of sine x. And this is how you notate limit. So you write lim, and then below that x, and then approaches, that's what the arrow means. It's approaching pi over 2 sine x. This is very important, by the way. The idea that it's approaching pi over 2. It's not of being evaluated at pi over 2. It's approaching pi over 2. And so what a limit means is that it's telling you what the y value or the output of the function would be as the x value is approaching this point. So for this sine function, because it's defined all the way through, we would it'll just be the same thing as evaluating sine at pi over 2, right? That just gives you 1. So the limit would be 1, right? However, that's not the case every single time. What do I mean? Well, I'm gonna bring back the concept of the hole. So you can have some function like this, and let's say it's not defined at x equals 1. And this function would be x times x. This is the same function we used before. This is the same function that we used before. Remember the one with the removable discontinuity at 1? But anyways, this function has a hole at x equals 1. Right? Now, what will be the limit as x approaches 1 for this graph? X minus 1, x minus 1. right? What would be the limit? Well, the limit is just limit. You cancel out the x minus 1, limit x approaches 1 of x, and then you just get 1, right? Simple. But notice how technically this graph is not defined at 1. So you're not evaluating the function at x equals 1. You're looking at the behavior of this function as x approaches 1. That is a key distinction between limit and evaluating a limit at a point. Now, keep in mind that not all limits can be defined. Example, remember when I talked about removable and not removable discontinuities? So removable discontinuities, there is a limit that exists, but non-removable there's not. So for instance, let's bring back the asymptote. I don't know exactly what function this is, but you get the idea. Let's say this is f of x, right? Let's say this line, this asymptote is at x equals 3, right? There's an asymptote at x equals 3. Now, if we say the limit as x approaches 3 of this function, f of x, what will be the limit? Well, if you look at both these curves, you know that they both go on infinitely downwards. Infinitely, they keep going until negative infinity. So you'd be like negative infinity. And that is correct. That's technically correct. But this is technically also the same thing as does not exist, because negative infinity is not a number, it doesn't exist. But you gotta be careful about when you write negative infinity and when you write infinity versus does not exist. These are both correct for this graph, but there are other situations where you cannot write infinities. You have to write does not exist. To give an example, let's write the same graph. Let's say you have some asymptote, and let's say instead this goes down, and then on the other side it goes up. Now let's say this x equals 3, asymptote. This, let's say this is f of x. For this one, limit as x approaches 3 f of x, this is always does not exist. Because we're not, see, 1 on the left side is going towards negative infinity, but on the right side is going towards infinity. And this brings us to the concepts of one, or I don't know the math term, I forgot, it's been a while, but it's left hand side limits and right hand side limits. And this will lead us to the definition of a limit. So, well, not the definition of a limit, but a limit can only exist if the left hand side limit and the right hand side limit are equal. They have to be equal in order for the limit to exist. Now, what do I mean? Well, let's say let's bring back our original graph. This x equals 1, right? And this graph is, I've wrote it many times before. If you were to calculate the left and right hand side limit, you can be like, well, limit as x approaches 1 from the right of this, you can see that from the right side, it's going towards 1. Limit as x approaches 1 from the left side, and by the way, this plus sign and this minus sign here, that just means right side left side. Left side is minus sign, right side is plus sign. But anyways, you can see on this graph from the right side, from the left side, it's also approaching 1, which means the limit exists. The limit as x approaches 1 is 1, right? Well, let's go back to this function right here. This function. Actually, let's not use this function. Let's use a different function. However, let's say you have a function, some piecewise function like this. Let's say you have a function that's defined until 0, then another function that's defined here. This is some piecewise function. Let's say that's like 1. So the piecewise function here would be x plus 1 from 0. Actually, it can't be defined on both points, so because that's not a function. Let's say, hold on, let's say there's a hole here. From 0 to infinity, and it's x from negative infinity to 0, right? So 0 is on this side, and 0 is not included on this side. But you get the idea. This is technically a well, not technically a non-removable discontinuity because it's not going to it's not a hole. There's clearly a big gap. But anyways, the idea of a limit is if we were to write the limit, let's define this as f of x. If we write the limit as x approaches 1 from the right side, let's see, from the right side, let's look at this graph. On the right side, oh, look at that. We're going to 1, right? So the limit from the right side is 1. Let's look at the left side. The limit from the left side is 0. Do you see? These two, the left-hand side does not equal the right-hand side limit. So the limit as x approaches 1 of f of x, oh sorry. Whoops, that's not 1, this is 0, I'm sorry. As x approaches 0 of f of x does not exist because the left-hand side limit and the right-hand side limit are not the same. Okay, so for now, I think I'll leave it at that. We will review more limit functions tomorrow, and then we'll also get into the limit definition of a derivative. So yeah, it's my first video. I hope you stay along. Goodbye.